Hello, I'm Joe Giuliano, and today I will be presenting Lab 3 circuits. Here's our introduction. So in this lab, we use DC and RC circuits to demonstrate energy conservation, and we use Kirchhoff's laws and Ohm's law to do this. And our result was two circuits, one DC circuit and one RC circuit, which were built. And we measured the behavior of a capacitor, and we discovered trends in our capacitance when it's discharging and charging. Here are our principles and models. So we use Kirchhoff's current and voltage laws, also known as the loop rule and the node rule, along with Ohm's law. And then our models are our macroscopic DC and RC circuits, along with a graph of the DC circuit's potential voltage. And here's our Ohm's law. So we have delta V equals IR, which shows the relationship between potential voltage, current, and resistance. And here's our Kirchhoff's voltage law, which is the loop rule. The sum of the voltage contributions in a closed loop equals 0. And for our current law, which is our node rule, we have the sum of the current in equals the sum of the current out. Here are our initial conditions. So on the left, you have the RC circuit, and on the right, you have the DC circuit. On the left, you can see that there are two batteries, two ammeters, and two resistors. And on the right, we have an example of an RC circuit showing the capacitor and the resistor, hence the name RC. And in our actual RC circuit, which we end up making, in our actual RC circuit that we end up making, we have a capacitor, two batteries, and two light bulbs. And so here's our DC circuit. We have our steps on the right, and you can see we have our ammeter, resistors, and batteries. And so our first step was to assemble the circuit, and then we collected data from our ammeters. So here they're I1 and I2 for our ammeters 1 and 2, and we got 17.7 milliamps and 17.6 milliamps for I1 and I2, showing the conservation of the current. And then we had to convert one ammeter into a voltmeter to describe the reading. So we got 17.8 milliamps for I1, which is the same. And we got 0 volts for I2. And then we measured the potential voltage or the potential difference across circuit elements. So we got 1.8 volts, 0.83 volts, and 2.72 volts for our different elements. And we summed those up to get 2.63 volts. And then a theoretical potential difference of 2.72 volts, which is the voltage across the battery. And we'll talk about why that's different later. And then we drew a graph. And here's our electric potential versus position graph, which shows the voltage drops across each resistor. Here's our RC circuit. So this was the second part of the lab. We set up an RC circuit, and then we observe the behavior of the capacitor charging over time. On the top, you can see the charging capacitor, and on the bottom, you can see the discharging capacitor. And so it took 5.41 seconds for the 10 ohms light bulb to charge, and 6.7 seconds for the 10 ohms bulb to discharge. And then we repeated that procedure with the 20 ohms bulb, and we got 32.4 seconds for a charge and 45 seconds for a discharge. And here's our what if. So if we charge the capacitor with no resistor in the circuit, we would immediately reach the target voltage provided by the battery due to the capacitor being critically damped. Now, we don't talk about critically damped capacitors in this class, but I wanted to mention it anyways. The ideal model would predict the capacitor to reach full charge immediately, but it doesn't happen in real life due to wire's minuscule resistance. And we measured this to be 3 seconds due to the addition of resistance from the ammeter and wire. And to conclude, we had two circuits, a DC circuit and an RC circuit, which were created to demonstrate energy conservation in circuits. In the DC circuit, the total potential difference was calculated to be 2.63 volts, but was predicted to be 2.72 volts. The calculated value was lower due to the resistance in the wires and ammeters. In the RC circuit, the time to charge and discharge the capacitor was timed and measured, and these trends the trends we discovered were that the capacitor discharges slightly slower than it charges, and that the capacitor charges and discharges much slower when the resistance is increased. And here are assumptions and sources of error, and that's it. Thank you.